Hello everyone, and welcome back again to the linear algebra component of the Calculus and Linear Algebra series. In the previous video we introduced the idea of a logical connective or logical operator, and we also introduced the unary operators. Those were the operators that took in a single propositional variable and mapped out a single propositional variable. But in this video we're going to focus on the binary operators, so that is the operators that take in two propositional variables and map out a single propositional variable. And in fact the binary operators are a lot more prevalent than the unary operators that we introduced before, despite the fact that they're a little more complicated. So let's have a look at a kind of portion of the binary operators. Well, unlike before where we only had 4 unary operators, there are actually 16 binary operators in total, and we're only going to define a small subset of those, just these 4 that we've got here. And the reason for that is it's just those 4 that are going to appear throughout this course, and these are mostly the ones that you'll also see in other courses rather than the other kind of versions of these binary operators. So let's go through them individually. So if we look at this first one, it kind of looks like a triangle with the bottom cut off. This is known as the logical AND operator or AND operator. And this is just the formalized operator for any propositions that contain the word AND. So if I have something is true and something else is true, then this contains that AND operator. Now the next one, as you might expect, which is the kind of upside down version of the logical AND operator, is the logical OR operator. So this is the operator, or the formalized operator, that corresponds to any propositions that contain the word OR in. Now the next one is probably the most used operator that you see in mathematics. You may have seen this before. It's also one of the most misused operators in maths. And this is in fact the implication operator. And what this is this is the formal operator for any propositions that contain things of the form, if something is true, then something is true, or the words hence or therefore. So what it tries to do is it tries to connect together two individual propositions by saying, say, the first proposition, if that is true, the next proposition is necessarily true. So it follows, that from the truth of the initial one, that the later one is true. And that's kind of how we can think of the implication operator in this case. And the last one we're going to look at, which is kind of a double-sided version of the implication operator, and we'll actually see in a later video why we use that notation when we introduce a notion called the converse. This is known as the equivalence operator. And what this allows us to do is it allows us to define whether or not two propositional variables or compound propositions are in fact equivalent. And where that's particularly useful in mathematics is suppose that I start with an initial proposition that's very difficult to prove. And suppose I recast that proposition into an equivalent proposition that's much easier to prove. Now if I prove this thing that's much easier to prove, because these two propositions were equivalent, that means that I've proved my original thing. So that's where this is going to be really useful, because I might start off with some initial proposition, I can massage it into something that is much easier to prove, which is equivalent to the initial thing, and then prove that later thing, which has now proved my initial thing. So that's why it's going to be particularly useful within mathematics. But like before, to actually define all these operators, we need to write out a truth table. Unlike before, we don't just have a single propositional variable now, because we're not working with the unary operators. Instead, we're working with the binary operators, and therefore we have two propositional variables as our inputs, and we've written them here as p and q. And we not only want to run over all the values of p and q, which are just true and false, but we also want to run over all the iterations of those. So that is p is true, q is true, p is true, q is false, p is false, q is true, and p is false, q is false. And using those, we want to define now what our logical AND operator or AND operator is. But when is this going to be true? That's going to be true when both p is true and q is true. So our first value here now is going to be true. And all the other values are going to be false, because in each of those cases, we don't have that both p and q are true. We always have at least one of them is false. So we find that this next value is false because q is false, this next value is false because p is false, and the final value is false because both of them are false. So what about our logical OR operator? Well, our logical OR operator is going to be true when either p is true or q is true. So it immediately follows that the first three values are true, because in this case they're both true, in this case p is true, in this case q is true, and on the final case, p is false and q is false, so they're both false, so that means that the overall OR operator is false. Now what about our implication operator? So recall that our implication operator we want to think of is when p is true, q is necessarily true. So we've got in this case p is true, q is true. Well, that means that our implication is going to be true, because that's what we want by construction of our implication operator. But what about our next case? We've now got p is true and q is false. But that doesn't really make sense for what we want, right? Because we want our implication to mean that if P is indeed true, that Q necessarily has to be true. So this next stage should be false. That can't be the case. And the final two are rather confusing. So you might think both of these are false, but in fact, both of these truth values here are true. And this follows from an idea that because P is false, a falsehood can imply anything. So in our kind of definition or idea of the implication operator, all we want to say is when P is true, Q is necessarily true. But if we're supposing that P is false, then that could imply anything. Q could be true, Q could be false. It doesn't really matter. So the overall implication is still true, which is rather confusing, but that's how we define our implication operator. And it's extremely important that we define it in this way, because what we'll see in a later video, that because we use these truth values on these last 2 points here, this allows us to show the equivalence between this implication operator and something known as the contrapositive of this statement. And we'll see that in a later video. And because of that, this allows us to construct certain types of proofs called proofs by contradiction. And you may have already seen a proof by contradiction in the calculus part of the course. And these are extremely powerful types of proofs that we want to use within mathematics. So we want to define the implication operator in this way so we can construct proofs in that manner. And the final one we've got is the equivalence operator. And you can think of that in some sense as the double-sided version of the implication operator. And as I said, we'll see that later in another video when we introduce the converse. And therefore that is going to be true only when P and Q have the same truth value. So in the first case, P and Q are both true, so that's going to be true. In the next two cases, they're not the same truth value. We've got a true and a false and a true, so they're going to map to false. And in the final one, we've got two values of false. Those are the same truth values, so therefore it maps to true. So that's how we define all our elements of the truth table for the binary operators. And the next thing to do is to introduce some kind of real statements or propositions that contain these operators, to give you some examples. So let's just look at the beginning at some examples of things containing the and or operator. So the first one we've got is I will either take the bus or the train. So this is a simple example of a statement or proposition that contains the or operator, because we've got a bus or the train in there. The next one we've got is tonight I will eat both pizza and chips. So this has the word and in, therefore we're using the and operator in this particular case. We've got here now the UK and US both belong to the United Nations, because again we've got the word and in there, we're using the and operator. And the final one, we've got an example here where now we're containing both logical operators. So we've got I will watch TV and either eat ice cream or chocolate. So this means that I'm using my or operator and I'm using my and operator. So this demonstrates that you can construct statements or propositions that have multiple logical connectives in. In fact, I could even have put a unary operator in here. So I could have said something like, I will watch TV and either eat ice cream or not eat chocolate, right? That's using an example of also having my negation operator in the mix there. But using this or operator gives us a particularly useful tautology that I kind of introduced in a previous video as an example where I said, my name is James or not James. And this is kind of fundamental to propositional logic. In fact, we're going to look at this as a theorem. So we'll see that this is always true regardless of the proposition that was put in there. So in this case, I've got P as a propositional variable, and I want to prove that the compound proposition P or not P is a tautology. So that's like my example I said a minute ago, my name is James or it is not James. That is obviously true. But I want to show that is true for any proposition that I can put into that. That's what this statement is saying here. And that fundamentally relies on the fact that a propositional variable must be either true or false. So how do we prove this? Well, recall that a tautology is something that if I take the valuation of that compound proposition, it is always true. So how do I take the valuation? I said it was neat to be able to use truth tables. So let's write out a truth table for this compound proposition. So I start off and I fill out what are my atomic propositions in this compound proposition. Well, the atomic propositions, the most fundamental pieces of it, are just P. So I look at my propositional variable P, and I just look at all the possible truth values of that, namely true or false. And now, what's the next kind of thing that I want to build in here? Well, the other component of this is not P. So what happens to the true values of not P? Well, that takes the value of true to false, and the value of false to true. So that's our value of not P. And then the final thing we want to look at is P or not P. Well, recall we've already defined the truth table for the OR operator, And that is true when either of the values takes the value of true. So in this first case, because we've got p is true, that's going to map to true. And in the second case, because we've got not p, or the negation of p is true, that's also going to map to true. So what have we shown here? We've shown that regardless of the values of p, the truth values of p, that p or not p is always true. In other words, it's a tautology. So we've taken the valuation of it, we've taken all possible values and shown that they're always true regardless of what the truth value of p is. So we've proven our statement, and when we've proven it, we write down this little kind of box at the end to say that the proof is finished. So that's what that means. And we've proven that it's a tautology. So to finish off, we're going to look at some more examples, and we're going to look specifically now at some implication examples. So recall our implication examples were things that of the form that kind of had if-then in. So this first one here, which is if the Earth is in the solar system, then it is in the universe. This is an example of something that has if-then, so it is an implication statement. The second we've got here is pigs can fly, hence they have wings. So the word hence here is the reason that we're using the implication operator. In this case now, if I am born, then I am human. Again, this is an if-then example, so this again contains the implication operator. The next one, we just got 1 equals 2, then 0 equals 0. So that's another example of using the implication operator because of the word then. And the final one, which is a bit more tricky and longer, we've got if a number is prime, then it is both odd and not divisible by any integer other than 1 in itself. So this is an example of one containing many different logical connectives. We've got an if-then statement, so it's containing the implication operator, and we've also got an and operator in there because we've got both odd and not divisible. So it's containing the implication operator and the and operator. And now what I want you to do is to pause the video for a moment and think about which of these statements are actually true and false. See if you can deduce those from looking at the truth tables that we defined a moment ago for the binary operators or for the implication operator. So take a moment to pause now and think about those, and I'll go through the solutions in just a minute. So hopefully you've taken some time to pause, and I'll go through the solutions now. So this first value here takes the value of true. Why is that the case? Well, let's look at our truth values of our individual statements. The Earth is in the solar system. Indeed, that is true. And it is in the universe, which is also true. So that's like P and Q is true, so our implication is true. Now, what about the next one? We've got pigs can fly, hence they have wings. Well, our initial statement, pigs can fly, is false here. And recall that for our implication operator, if the initial statement is false, then the overall implication is true. So regardless of the second statement, whether or not it's true or false, the overall thing is true. So this thing is true, which is a bit surprising. So this is an example of a falsehood implying a falsehood, which overall is true. Now the next one, we've got if I am born, then I am human. Well, in this situation, I could have a truth. I could be born, but I could not be human, right? I could just could take another animal on the planet. So this is an example of a false statement because I've got a truthhood implying a falsehood, so therefore it's overall false. On the fourth one now, we've got 1 equals 2, then 0 equals 0. So again, this is another example where the initial statement is false, and because the initial statement is false, regardless of the second statement, the overall statement must be true, or the implication statement must be true. In this case, we've got a falsehood implying a truthhood, right, because 0 does indeed equal 0. And the final one is a little tricky, because I've got if a number is prime, then it is both odd and not divisible by any integer other than 1 in itself. This might seem to be true, but we've got this small edge case, which is the number 2. That's an example of one which is divisible by 1 in itself, but it is not odd. And because we've got the and operator in here, recall that the and operator is only true if both of those conditions are true. So this overall statement here is false because we've got a truthhood implying a falsehood for the one counterexample of the number 2. So that's where I'm going to conclude the video. And in the next video, what we're going to do is we're going to look at constructing some more tautologies, some more theorems of tautologies that will allow us to construct certain types of proofs that are called deductive proofs. And these are going to be particularly useful throughout the mathematics that you do, right? That we want to be able to deduce something is true given some conditions. So thanks very much for watching the video again. And I would say again, please look on Moodle for the notes that you can watch after this video, and I see you in the next video. Thank you very much.